Great. So we are continuing the probability theory. We discussed a little bit about probabilities. We talk about the basics of probability theory, especially these three axioms. That these are the only thing that the main base of probability, and everything else should come from that. For example, these are some of these propositions that we discussed, and this one that we mentioned that you can prove it from these guys by induction. So these are like the basic stuff about the probability. And in particular, we talk about the probability as an important tool for randomized algorithms and randomization. Whenever we have the randomization in our algorithm, we need to use probability to prove some guarantees on that. So that's the idea that we are using probability, and we discuss probability. So it's very important, and it's also almost everything nowadays in data science or machine learning or anything or algorithms they are working is actually based on randomized algorithms. And it is interesting, randomized algorithms are the type of algorithm, but there were some time, for example, approximation algorithm, maybe less hot, like as compared to 20 years ago. Still the concept of approximation is there, but maybe it's a bit different. But randomized algorithm that has been hot all over the time. And lots of algorithms, this is the one live that we had it with Professor Shiraz, and that's a very important one. I think you should take a look at it. That's a good one that, I mean, lots of places, even like whole AWS, lots of this hashing, etc. All of them are based on this concept of randomness. So it is very important that you know randomness quite well, and you can use it to prove guarantees for the algorithm that you may have. Okay, so we talk about the joint probability. Essentially means that this is the probability of A intersection B when you have two events. And we talked about the concept of independence. It means that essentially when some event A happens, then it does not changes the probability that B happens, either go up or down. We talked about the conditional probability. That was important because of this Bayes rule. This is the things that when we know about the prior and when we have about the likelihood from the history, then we can get the posterior as part of an inference. And that's the important one. We talk about this nice, essentially, example, the ball example. And we mentioned a bit more complicated version of that you can actually define it. This is the one that even this will be used. I have seen such kind of things in interviews, actually, that the people will ask to know that you know enough probabilities. Good. Now, the next thing is about the random variable and probability distribution, expectation and variance. These are also very important. Good. Let's define first a random variable. What is a random variable? So random variable is generally is a numerical outcome of a random experiment. So we can define actually random variables as much as we want, because that generally that helps us to analyze the algorithms. But we should define, I mean, we should see anytime that we can define a good random variables, we can do that. And it would be good to define random variables for simple stuff, such that we can then use sum them up or something like this to get a result for more general version. So in some sense, the rule of thumb is that you try to define random variable for any simple event essentially, or experiment. So what is a distribution? The distribution of a random variable is the collection of possible outcomes along with their probabilities. So you have defined essentially a random variable. It can take different values. And again, because it's a random variable, I mean, there is some chance that gets any of these values. What are the probabilities of that these random variables be? So maybe it's the random variables, I don't know. This is X, and it takes the values 1 to n, say. So these are all values that it takes. Then we have that what is the probability of essentially P of 1. Then what is the P of 2? 2 P of n. So if this guy is just can take the this kind of discrete numbers, 1 to 2 to n, this is the one that actually you can, for example, get from in Python. There you can get, I mean, the numbers like integers from 1 to n. And then the question is, what is the probability of each of them? Like P of 1, P of 2, P of n, and so on. And the important thing is that if these are just the integers, the sum of these PIs. So here, sum of these PIs should be equal to 1. That's the whole thing about the distribution. So in the discrete case, I mean, as I mentioned, we have just say that probability of x is equal to x. We are defining it by probability of theta of x. Where this theta is, in some sense, is a distribution. So this is a distribution theta. In the continuous case, you cannot say a particular point, what is that? That's essentially similar to integration. You need to always do the integration. You can say from in a range A to B, what is the probability of from the A to B, and that would be the integration of this guy's this. So in some sense, you can think about it if it is some like this is the probability distribution from, I mean, this is this guys to this guys. So if it is from here to here, this is so if you want to say this is A, this is B, this area, this probability would be essentially the area of this below on their curve. And that is exactly the concept of integration. What is the area that this area is essentially corresponding to the probability that x happens to be between A and B. Again, when you have this one, you cannot say in the continuous case, you cannot say probability of A because probability of any point would be 0 because of the integration on A to A would be always 0. What is the support of a discrete distribution? Support of a discrete distribution is set of all x for which probability of x is equal to x is greater than 0. So support is important. It might be the case that, I mean, this distribution, for example, here, it might be it is 1 to n, but only this happens that the x only takes the value 1 and n, for example, nothing in between. In this case, the support of this distribution would be 1 and n. P2, P3, P4 to Pn minus 1, all of them would be equal to 0, and they will be not part of the support. Finally, we also define the joint distribution for 2 random variables. So again, the joint distribution for 2 random variables is very similar to the one that we had a joint probability. It means that for 2 random variables, x and y, a collection of possible outcomes along with the joint probability. What is the joint probability? When we talk about it, is that probability of x is equal to x and probability of y equal to y. So this actually, you can, I mean, in some sense, if you just say about the probability distribution, so if x can just take these values, and you can just consider a one-dimensional array or matrix, and then say this is the probability distribution for different values 0, 1, 2 to n. You will write the probabilities here. These are the probability. So actually, in a distribution can be represented by simply by an array. For the discrete case, at least, you can just say what are the values, or actually you can use even mapping for that or dictionary. For all of this, you will say that, and you will say what are the probabilities. And the important thing is that sum of these probabilities is equal to 1. Now, what about joint distribution? So the joint distribution, actually, it would be a 2-dimensional matrix. You can have, if you have 3 variables, you can have 3-dimensional as well. So here, this is for x, and this is for y. Good. Then you will say x equal to 0, 1, 2, 3, 4 here, and then y is equal to 1, 2, 3, 4 here. And then here, this would be essentially P of x equal to x and y equal to. Again, the most important thing is that some of these probabilities. Oh. Let me just exit this mode. Stop share. Let me just. Good. Yeah. So the important thing, as I mentioned, so we have this we had this one-dimensional case. Some of the probabilities here was equal to 1. Some of the probabilities were equal to 1. When you have this two-dimensional case, again, the sum of this probability over the whole matrix would be equal to 1. So here, this is so a joint distribution, a distribution would be sum of these values equal to 1. A joint distribution over everything in the matrix, you can consider it like a two-dimensional surface essentially. Over everything should be equal. The same thing, like you may have a three-dimensional thing, then you can consider essentially three-dimensional matrix. And then sum of all the probabilities in this, all the numbers inside the matrix, some of them should be equal to 1. And that's very important when you have this joint distribution, because one of these events will happen essentially. Good. So that's a very important thing. That again, so it's not the case that, for example, sum of each row is equal to 1. No, this is not correct. Sum of the whole matrix would be equal for a joint. Good. Now let's define some random variables and some examples here. Let S be set of all sequence of 3 rolls of a die. So you consider all sequences of 3 rolls of die. Let X be the sum of the numbers of dots on the 3 rolls. Good. So you have essentially a sequence of 3 rolls of a die. You have it, and you have the numbers on the top of that. So the question is, what are the possible values for X? So what are the possible values for X? Here's the sum of these numbers of dots on the top. 3 to 8. Now, what is the probability that X is equal to 3? Of course, it would be 1/6 that is equal. So the X equal to 3 comes only when each of them is 1. That's the only case. So what is the probability? The first one is 1 is 1. If 1/6, the other one 1/6, the third one 1/6, 1/2. What about X equal to 5? What is the probability that that happens? What is that?
Is it 1/36?
Why?
So 5 only occurs when you have 1, 2, 2, or 1, 1, 3.
Okay, we have 1, 1, 3, 4, 2, 2, 1. Correct? Any of them can happen.
Yes, and there are 3 permutations for each.
3 permutations for each, yeah. because I mean, this essentially is because two of them are this. Three can be in the middle or at the beginning here. This one can be in the middle or at the beginning. So there are three here. So it would be six things, 6 times 1 over. So it would be 6 times 1 over 216. That would be 1 over 36. 1 over 36. I trust you on that. Good. So you can have that p x equal to 5, x equal to 6, and so on and so forth. What about p x equal to 18? 1 over, yeah, because the same thing essentially. It would be all of them should be 6. So you can compute this one. That's a good exercise. Good. Now let's define the expectation. For a random variable x, by the way, this is the thing that when we say that x comes from, sometimes this we say that this comes from theta. So this is the distribution essentially. X, this is the notation that x comes from this distribution. Then the expectation of x is x. So for it, so you are good. Do you see it now?
Yes.
Yeah. By the way, that's a mention. When you see something, mention to me right away. You didn't need to wait that much. Good. So here, yeah. So I mentioned about this joint probability. Let me just do this one. Okay. So I talk about the joint probability just briefly. That I mean that if this is just if it's distribution, this is one-dimensional array. If joint distribution, it is two-dimensional array. Do you see my writing now?
Yes.
Great. Okay. So in this case, so there was some person. Oh, sorry. Yeah. I mean, if something happens, don't send a chat. Just unmute and mention. That would be better. Okay. Yes. So when we have this two-dimensional things, then sum of this probability over all things would be equal to 1. And that's the thing that we discussed about the joint probability. Now, if we discuss about these particular things, if we have a sequence of 3 rolls of a die, what is the probability that some of these numbers of the dots on the 3 rolls for each value of x? So if x equal to 3, it means that the numbers on the top should be 1, 1, and 1. And for each of them, the probability is 1 over 6, so we get 1 over 216. If x is equal to 5, then the top guys should be 3, 1, 1, or 2, 2, 1. And there are 3 permutations of this and 3 permutations of this, and each of them has 1 over 16, so it would be 6 times 1 over 216, which is 1 over 36. And if you want to say x is equal to 18, then it means that all these numbers should be 6. So it would be again 1 over 6 times 1 over 6 times 1 over 6. And in general, the range of x would be from 3 to 18. So if x is the sum of these 3 guys, would be between 3 to 18. So now we will go for expectation. So do you see the screen, correct? And you hear me? Good. So if something happens, just let me know immediately. Don't wait, don't send chats. Unmute and mention. Good. So expectation. So what is a random variable x from this one? Here, as I mentioned, this is a theta that we are doing that. So theta is the distribution. When we say that x comes from this probability, x equal to x, or come from theta, then it means that x comes from this distribution. Then its expectation is equal to this. The expectation of x is equal to sum over all x, probability of x is equal to x. Good. So expectation of x is equal to all possible x. What is x times probability of x? So in an empirical sample, when this is like essentially it is called or a uniform sample, the probability of each guys essentially would be 1 over n. So in this case, would be 1 over n times sum of this number. This is somehow the average numbers. That's the figure that you can think about it. So if in the empirical samples, essentially it means that what is the average of these numbers? And in the continuous case, you need to do just the integration. Now you need to take the integration from minus infinity to infinity, x times p of x that comes from distribution theta. In the discrete case, in some sense, the average expectation is just the weighted average. It means that each what is the average, but if each of them have a different probability, then you just do the weighted average. It means that each of the weight times the probability, weight times the value over sum of the weights. Very important property of expectation is that sum of random variables. So expectation of sum is equal to sum of expectation. Expectation of sum is equal to sum of expectation. So we are, this one called also linearity of expectation. So linearity of expectation. So let's see some example. Let S be set of all sequences of 3 rolls of a die, the same thing that we had it before. And X be the sum of the numbers of the dots on the 3 rolls, the top of them. The question is that what is E of X here? What is the expectation of X here? So is the problem clear to the people at Zoom? So these numbers, X is the random variables, taking the values from 3 to 18. The question is what is the expectation of X? What it would be the... Why 3.5? Why?
So it is the expected value of the sum. So it's the sum of the expected value. Each row of the dice expected value would be 3.5.
Good. So here, I mean, if you don't want to do that, it would be hard because you need to say that, I mean, you cannot at least answer it very fast because you need to say that what is the probability that X is equal to 3? We had 1 over 216. What is the probability that X is equal to 4? You need to compute it. And then you need to say that, so for example, as I mentioned, so X is equal to 3. We had it 1 over 216. X equal to 4. The probability was what? Would be 211, would be 3 times. Then X is equal to 5 was equal to 6 over 216, and so on and so forth. So to compute it, you need to multiply these guys and then sum it up. That would be the expectation of X. But that would be hard. Another way is that, as I mentioned, try to define random variables for experiments which are as simple as possible. Here it says that, okay, we have a roll of 3 die, 3 rolls of a die. Let's define X1, X2, and X3. These are the 3 random variables which are on the top of this die. So, and then what is X? So X here, it is nothing than essentially is equal to this plus this plus this. Good. Note that here I have simplified. I have defined some. This is always like it makes the life much easier if you define this kind of random variable for the simplest events or simplest experiments. So in that case, X is equal to that. Now you can just what is E of X by linearity of expectation? E of X is equal to sum of the expectation. So it will be E of X1 plus E of X2 plus E of x3. Now, actually, we know that. So what is the one other thing is that we know that x1, x2, and x3 are the same thing. So E of them are equal. What is the expectation of one number? So then the number for one dice would be essentially 3, 4, 5, 6, 1, 2, 3, 6. Correct? These are the numbers that can take it. And this is the uniform case. So if it is no bias, so the probability of each of these guys is 1/6. So it means that in this case, you only need to take the average of these guys. What is the average of these guys? Essentially, you can say that 1 plus 6. You can just sum it up, or this guy and this guy. Average of each of guys would be 7. So the average of these two guys would be 3.5. Average of these guys 3.5, and so on and so forth. So you can see that actually you can sum it up and see that the sum it up and divide it by numbers would be 3.5. So then here it would be 3 times expectation of x1, because these are all the same, which would be 3 times 3.5, which is equal to 10. So the solution here is 10.5 for expectation. Now let's see, change the experiment. Say, let S be set of all sequence of 3 rolls of a die, the same experiment, but X be the product of the numbers of the dots on the 3 rolls. Good. What is E of X? Yeah. No. So that's the thing. So it is called linearity of expectation. We have these rules for only, so you can still define it. So you can define X is equal to X1, X2, X3. These are the things. And then X is equal to actually X1 times X2 times X3. So everything is fine. But the issue is that we don't have these things that E of X is equal to. So this is not necessarily, it might be correct for some case, but it's not necessarily correct that it is, you can multiply these guys. So this is not necessarily equal. You cannot use that. Yeah? Sorry, what was that? We don't have any formulation, I mean, like a typical thing. So in this case, the way that to do that, actually, you need to see what is X. So like, for example, if you can think about if, what are the possibilities for E of X that can be essentially, like if all of them are equal to 1, then in this case, what is the chance of that? Would be essentially 1/216. And in this case, that would be 1, the multiplications. Then you need to compute it. What about if it is 1, 1, 2 is coming, for example? What is the chance would be essentially, so how many things would be 3 times 216? In this case, this multiplication would be 2. And so on and so forth. You need to consider all cases and do that. You can think about how can you do it more efficiently, but at least you cannot just simply multiply these numbers and get the result. Good. So that's a good exercise for you to do that. Another thing which is important, the variance. So variance of a random variable X is the expectation of X minus E of X to the 2. Good. So what is the variance? The variance of X is equal to expectation of E of X minus E of X to the 2. So variance is typically is like we have, this is the standard deviation. Standard deviation would be essentially root of variance. So what does it say? So this variance essentially is somehow for risk aversion. So if you have some variable X, then you know that the expectation is here. So this is the value that it gets. But the issue is that you want to see how much, what is the expectation of, what's the concept of essentially variance? Variance, and this is called a standard deviation. So what is a standard deviation? So generally, I mean, a standard deviation is this one. So we know that this kind of the expectation of X is this one. But the issue is that this any random variable that you may happen. So this is the E of X. You want to see what is this may happen that this guy is not exactly here, but this random variable that you have, it happens here, it happens here, it happens here. You want to see what is the expectation of this part from this. So with this number, what is the expectation of when these guys are coming comparing to their expectation? So what is the range that these guys are coming? That's essentially the one that you're talking about. Here it is E of X, X minus E of X to the 2 for variance, but we have this standard deviation, which is essentially this guy. So this standard deviation, it tells you what is the expectation of the difference of these guys from their average. So this guy talks about the average. This guy said that what is the range that these guys are coming from here, and that is called a standard deviation. Okay, so what is the, as I mentioned, so the exact definition, so variance is actually X minus E of X to the 2. So it is this one to the 2. Standard deviation is essentially a square root of variance. Just X minus E of X. So what is the variance? So variance of X? Variance of X is expectation of X minus E of X to the 2. So that's a good example actually to work with expectations. So let's do that. So X minus E of X to the 2, we can just, I mean, essentially expand it. It would be X to the 2, E of X to the 2, 2 times X E of X. One important thing, E of X to the 2 is a number. So this is, so E of X is not a random variable. E of X has only one value, which is there. So E of X is just number, like number 2 or 3. It is not a random variable, very important. And then expectation of, what is the expectation of a number 2, for example? What is that? Is 2. So expectation, I mean, or any constant C, expectation of that would be just C. In particular, expectation of X is equal to just expectation of X. Because there is nothing random there. It's the expectation of 2 is 2. I mean, there is no randomness here. So here, and here first we are using the linearity of expectation. It will be equal to E of X to the 2. Then E of X to the 2 would be E of X to the 2 because this is because of this formula that I mentioned, it's just constant. Then we have 2x E of X. And this is also important. When you have so what is this expectation of E of like essentially minus 2x E of X. So this minus 2 and this guy, these are just some constants. Constant always can come out of the expectations. So it would be, so if we have this one, we have, that can come just minus 2 E of X. And then only thing that remains would be expectation of X. That's exactly this formula. So any constant can come essentially out of the expectation. Good. So now we have this one. We have E of X to the 2 minus E of X to the 2 minus 2 E of X to E of X. But this one is equal to actually minus 2 E of X to the 2 as well. So we have E of X to the 2 plus minus 2. It would be minus E of x to the 2. So it would be E of x to the 2 minus E of x to the 2. So then just the 2 is important. 1, 2 is inside the expectation. The other one is outside. This is, yeah. So that's essentially the definition of variance, as I mentioned. This is, variance is the one that, then if you take the square root of that, it would be a standard deviation. That would be the one that says, what is the expectation of these guys, the range of the interval that they come around their expectation. So in some sense, if it is the case that this standard deviation is very essentially is small, it means that the variance is small or standard deviation is small. It means that these guys are very concentrated around their E of x. So you know that it is the case. So it means that this is not a risky thing. So you know that it is around the E of x. But if the variance is large, it means that it can be all over the things essentially. So it means that, I don't know, if you bet on these things, you can possibly lose a lot because the variance is high. Good. Now let's define some important formulas here. So one is the Bernoulli distribution. So this is the outcome of an experiment that can either be success means 1, or failure, which can be 0. What is the things that we have here? For example, we have this. Probability of x is equal to 1 is equal to p, and probability of x is equal to 0 is 1 minus p. Or you can define this probability, if you want to write it in a formula, you can write it this one. P to the x times 1 minus p to the x. And again, x can take here the value 0 or 1. So if you put x is equal to 0, then this guy becomes essentially 1. This becomes 1 over 1 minus p. This is the case. And if you put x equal to 1, then this guy becomes 1. And then this one becomes p. So you can say that it's a probability this, or you can just get this. So what is the expectation of x? So expectation of x is equal to p. Why? Yeah. Yeah, so x is equal to 0. The probability would be 1 minus p times 0 would be 0. And the other case would be x equal to 1. Probability would be p. So 1 times p would be p. That would be a simple thing. 1 times p plus 0 times 1 minus p. What about the variance of x? Variance of x is equal to e of x to the 2 minus e of x to the 2. Good. What is e of x to the 2? P squared. What is e of x to the 2?
Because it is 1 with probability p and 0 with probability.
Yeah, actually x to the 2 and x are the same, because if 0 to the 2 would be 0, and x to the 1 to the 1 would be 1. So e of x and e of, here in this case, e of x is equal to e of x to the 2 for these guys. So it means that essentially p minus v would be this. So this is another formula that we have it actually here. This is a binomial distribution. That's also a very important one. This is end rows of Bernoulli distribution. So here, xi is say Bernoulli. So xi, this is the one that we are defining xi to be this guy. So this should be n actually here. So here it says that I equal to 1 to n, sum of xi, where xi is a binomial, is a So X is a binomial distribution. They represented by P and N. And each of them, N is the number of N rows. And then each of them is Xi is is a Bernoulli thing. So if you want to have the formula, so what is the probability distribution of this? That would be equal to this one. It would be if X is equal to 1, 2 to N. So this is essentially, we say that like X can be like one success. What is the probability of one success? You can choose where is this one success that for that we have and choose one. And then this one success one would be P to the X because we have one success. And then all others guys would be failure, would be 1 minus P to the N minus 1. In more general case, if you have X success, it would be the same thing. You have X places that you need to say, where are these successes? What is the probability of them? X. And all others should be negative. It should be failure. So do 1 minus place to the N minus. So this is the probability distribution. Now, what is E of X? Is NP. Why NP?
And Bernoulli distribution.
Yeah, what do you want to say?
X is the sum of time.
Yes. So each of them is xi, and we have this just using linearity of expectation. The expectation of each xi is equal to p. So we have n of them would be n times p. Variance of that is n times p times 1 minus over p. So that would be a bit harder because you need to compute e of x to the 2 minus e of x. E of x, of course, we know is np. But what about e of x to the 2? That is not so simple. You need to compute it, actually. You need to use this formula to compute. However, one interesting thing here was this one. So what was the Bernoulli variance of x? Was p times 1 minus p. Correct? So what was p times 1 minus p? The variance of x for Bernoulli. Here, interestingly, it is n times p times 1 minus p. So it seems that we have linearity of variance even here. So this is somehow linearity of variance. And that is interesting. Why? Actually, we will talk about it later. We say that actually binomial distributions and Bernoulli distributions. So this is and Bernoulli distribution. Both of them are normal or Gaussian distribution. Good. For normal or Gaussian distribution, we have not only, we always have linearity of expectations, but for them also we have linearity of variance. This again, these are the standard deviation. Sigma is standard deviation. So if we have this, we know that Bernoulli and binomial, these are actually a special case of this kind of normal distribution. For normal distribution, that's a good thing. We have the linearity of variance. So in general, what is the formula for these guys? this is the formula for this. Actually, this should be, I think this one should be floor of this guy. So that would be the formula for that. So what is the normal or Gaussian distribution? It is this one that for this one, for a normal distribution, we need to know exactly two things. One is the mu, and the other one is sigma to the 2. So the normal distribution generally are something like this. These are the normal distribution. And it can be, I mean, extreme cases like this, or like some other things like this. These are all normal distributions. But generally, it is two things is important. One is mu, which is the expectation. The other one is this standard deviation. If I remember correctly, the probability that it happens is something like this one is 0.66 would be something that is like in the standard deviation. If you go to here around sigma, the space here is, so essentially 0.66 probability is already when you go around mu and then you go sigma here and sigma here. I think if you go 3 sigma here, then it would be almost 95% or something like that. So if you go to 3% here, so the integration of here, this area would be essentially 95, like 0.95. You can double check this. But anyhow, so this is the formula that we have it. This is 1 over this 2 pi sigma 2 to the expectation of x minus mu to the 2 over 2 sigma 2. And here, this is this one, and then probability of this guy, you need to just do the expectation, which would be this guy. So expectation of x would be this, variance would be sigma to the 2. So in some sense, the normal distribution is determined actually by its expectation and variance. That's the only thing that you will say that and decide that one. And if you have 2 variables, which are both of them are essentially normal distribution, so when you sum it up, not only this probability, the expectations will be sum it up, the variance will be sum it up. And again, we have used this one to get that variance for that formula that I mentioned. So this is so here I have just used linearity of variance since this Bernoulli's are normal. So if you look at it, it would be like this. So plots of binomial distributions. So if this is something for example, p equal to 0, 1, and n equal to 100 would be like this. This is exactly that I mentioned. So there you decide what is the mu, which is the things, and then what is this sigma, or sigma to the 2. So for p equal to 0.25 and n equal to 100, it becomes like this. P equal to 0.05, then it becomes like that. And 0.25 would be a reverse of that, would be like this. All of them have this kind of Gaussian or normal distribution. Another important one is the Poisson distribution. So a Poisson distribution is the one that is coming from binomial distribution when we say that we are fixing the expectation to be n times p. And let n goes to infinity. So Poisson distribution will be determined only by so Poisson distributions would be only determined by their lambda, which is n equal to p. So you are equal. So binomial had 2 parameters, n and p. Here we are assuming that n and p would be always lambda, and then you assume that n goes to infinity. So that would be the probability would be essentially, you can write it down, probability of x is equal to x. It would be lambda to the x over x factorial e to the minus lambda for x greater than 0 and 0 otherwise. One important property of this that both variance and expectation of this would be lambda. So Poisson actually will be used. It is something which is called memoryless distribution. That if like the fact that something happened in the past doesn't increase the probability of that the things happening now. You can actually read more about it, this memoryless property of Poisson distribution, and then you can use it. It's here. I want to just give you a short summary of that. But again, if you consider lambda equal to 5, that would be like, again, this type of things. Lambda equal to 15 would be something like this. And lambda is, again, this is the, you expect that if lambda equal to 5, it should be around 5, correct? That's by definition, because the lambda is actually the expectation. Lambda equal to 15 would be around 15, symmetric around 15. Equal to 25 would be around this one and this one. So this is also another normal distribution. Actually, here, I think this was the formula for this. So just forget about this one. So this is expectation of these guys. So 1 over 2 pi, yeah.
I think it's not expectation, it's exponent.
Sorry, I meant exponent. Yes, yeah, thanks for. Yeah, so this is exp I mentioned for yeah, expectation. So here it is exponent. So it is essentially e to this number, x to minus mu to the 2 over 2 sigma 2. Yeah.
But for the Poisson distribution, like you sum over the system limits for how do you know that that thing is the order of $30 and
Where?
in one sort of the Poisson distribution?
Yes.
When you let the number of Gaussian infinity.
Yeah.
When you're calculating probability of these facts, how do you know that the expected value will be X?
I mean, this is the one. So always I define the parameter lambda to be equal to NP. So that is by definition, lambda is equal to NP. So here it means that if N goes up, then P should go down. So that's the thing that I mentioned. So this, like I say, I mean, it might be better. This is just some kind of intuition. You may just consider this particular formula, which is lambda to the x over x factorial e to the minus lambda. So if you get this formula, from this formula, you can get all of this other intuition. In some sense, it's better to just think about this, and then you see why. Because this is like, you don't need to define it this way. This is just some intuition. This is the actual probability, and you can say that this has this property. Lambda is equal to that. E of x is equal to lambda. Variance of x is equal to lambda, and so on. And this is just more intuition. But there are some good properties. You can just go and read it in Wikipedia and others about Poisson distribution that has actually lots of good properties. But as you will see, actually, this is also a normal distribution, and this is the one that you have mentioned. So this is essentially exponent of that. It means that e to this number. And it would be good. So for example, here, you can just put, if this is the case, you can say it is both, you will put normal distribution would be lambda, and you will put this one and see you should be able to get the same P for this. But yeah, so this is the most interesting one, essentially. So it is e to the minus this guy. This minus is important. The other guys is just. So e to that number. And it has this property. So if it is a normal distribution, we have linearity of variance as well, which is a useful one. Good. And so last thing, I think we want to talk a little bit about the probability in Python. So if you want to use the probability in Python, that's the one. So these are some important ones. You need to use numpy. Is an important one. And numpy.random, this is the one that you can just use it for. So here, yeah. So this is, we say numpy as this one, and the other one, numpy. .random as Rn. So here you import numpy.random as Rn. So this is for random instances. And then NP is the one that, the general NP. And this other one, the scipy.stats as ST. This is some of this more, so in some sense you can consider scipy as extension of numpy. Numpy is the one that is implemented in C++. It's very fast, and the whole thing is considered essentially the matrices. It's just very fast for matrices. You can have one-dimensional, two-dimensional, or like n-dimensional matrices. And the important thing is that these matrices, all of them should, all the values should have the same type. That's important. And these are some limited types. So like, for example, the integer in Python can have arbitrary lengths. In NumPy, it is not like that. You need to say that if you say NumPy, you should say, what is the maximum length of this? Why? It is essentially less general, but it's much faster. So if you can do something with NumPy, you should be able to do NumPy. So here, for example, I mean, this is just some example. I will define array 1, which is NP full of 4 and 3. So it defines essentially an array of size 4, and all of these numbers are 3. Inside is 3. So this is the number that I mentioned. So this is an array, you can define it. Anything that you have, actually, you can change it to an array. Generally, you will say, if you have something, you will say np.array of some list or array or some regular thing in Python. But you need to see that if you have a list, that list, if you have 2 types of things, then it may give error essentially. If all of them are the number, then it can turn it into that. Then this is the sum of this that you can generate. For example, here, you want to you are defining x to be 1000. Good. So here, this is the, you will say that rm.randn. Randn is the one that is for normal distribution. So that generates a normal distribution. Here I mentioned another example, rm.randint. Randint essentially, then this one is a range. It says that between 0 and 2, and the size of that should be 20. Good. It says that it generates some numbers, random numbers between 0 and 2, and the size should be 20. So the size is 20, and the range is between 0 and 2. It means that 0, 1, and not 2 included. That's a typical thing in the range that we are talking about. When we say range is 0, 2, generally means 0, so 0, 1, and not 2. 2 is just like, it is like this. So it has closed things here, but it is open. So it generated these random numbers for you, and 20 of them. Size is 20. Here, this is the one rand n 20. It means that generate 20 numbers for me. This 1000 times this, that would be actually the standard deviation. So when you multiply this guy, so this is generally between 0 and 1. But then you multiply this one. This is a NumPy thing. When you multiply 1000 times an array, that every number is between 0 and 1, just multiply every element of that array by 1000. So this is actually the 1000 become a standard deviation. What is the expectation here? The expectation is this 10,000, because you will say that also plus 10,000. When you say plus 10,000, each element of that array will be plus 10,000. So this is this operations that we can do it with NumPy very nicely. We say one element times this array, it means that essentially multiply every element of that array. If you say this array plus some number, it means that every element should be added with that number. So here we are having a 1,000 as a standard deviation, and then this 10,000 would be, this one would be essentially expectation. So here it is the one that we are getting it. We get an array of size 20, and you see all of them are around 10,000 with some noise, random noise. Yes?
So if random and gets a number between 0 and 1,
yeah.
Then what wouldn't be? So then that means like no data point would be greater than 1,000 away from the mean.
No, sorry, when you say rand n, yes, sorry, rand n generates something between -1 and 1. So rand n, it generates some number between -1 and 1 with expectation 0.
If the sum of the numbers be more than 1,000 away from the normal distribution. So
it would be, so at most would be 1,000 times 1, 1,000 times 1, or 1,000 times -1, correct? So that you will see some of them are essentially these 10,000 plus 353, that's a plus part, or some of them are 987, it is less than 10,000.
In a normal distribution, data points be more than 1 standard deviation away?
Yes, but yeah, actually, you're right on that one. You see, this number is like this. So here, I think I need to clear this one. So this, yeah, so this is this. When you say rand n, means essentially the random with standard deviation 1 and around expectation 0. Thanks for the clarification. So you can, these are exactly the definition, you can see that. But this random, the expectation would be 0 and the variance would be 1 essentially. Or the standard deviation would be 1. Generated then 1,000 times that. And this is the address. So there are some other things that are interesting here. For example, these are the ones that you can get it more from this scipy.stats. So these are some of the correlations. So you can get there are two definitions of correlation. One is the Pearson correlation and the other one is a Spearman correlation. You can see the definition of these guys at like, for example, Wikipedia, the exact things. But these are actually important. So you can actually, for example, what did I do that? I can, so this is one thing, I define this one. Correlation 1. So I defined, so these are the D1 and D2. I defined it as two vectors. And then when I defined it as the 2 vectors, then I have defined, say, I say that what is the correlation of the Pearson? The Pearson is the more like the standard one of D1 and D2. So this is one vector that I have it. The other one is I have this other vector that I have it. And I will say, what is the correlation of these guys? And what is the meaning of correlation? For example, if this is like this one, so if you have one matrix is 1, 2, 3, the other one is 2, 4, 6. If this is the D1, this is the D2, then actually you will get perfect correlation of 1 here. If it is -2, -4, -6, then you get a, so here, if it is -1, the correlation becomes -1. So generally correlation 1 and -1 means perfect correlation. It means that these guys, they have correlated. That will be very useful for data science, because in data science, you have essentially, you can think about, you have a matrix. Some of the entries you have, some you don't have it. And you want to fill in the holes. If you have correlation between some things, then it gives you some idea that how you should fill in the holes. So correlation is a very good thing in that sense. Correlations are not always good. So for example, if you want to get sometimes independence is good, but for data science, generally correlation is good, because that correlation can help you to fill in the empty holes in the matrix that you have, or for those values that you don't know. Those values you want to predict, You can get it actually from correlation. So correlation 1 and -1 would be good, and anything which is less correlation would be essentially between -1 and 0. Essentially 0 means almost independent. So here, between this, I have generated one random things and the other one, two random things I have generated. So the correlation that I got it, especially the Pearson one, is this one. 0.130, this one. And I mean, Spearman is another one that is defined. I mean, essentially, the general is some kind of extension of Pearson. You can read more about it, and then you can actually see that one. But this is the one that you can get it in Python. So I don't want to go through that. I mean, the more details. I just want to say these correlations are important. Scipy and numpy random and numpy are very important for if you want to use them in Python. There might be some libraries in C++. I don't remember it on top of my mind, but there might be similar things there. But in that case, actually, Python is very strong. For this, all of these calculations you can do. Good. So let's stop share. Good. So I think that's it. So we are done essentially with the probabilities and expectations. Now, next time we talk about some other algorithm like hashing or quicksort. These are the randomized algorithms. And for them now we have the probability knowledge, so we can go and discuss the exact running time or the performance or anything. If there is no other question, we can just finish that and then see you next session. Okay, bye.